All right, welcome to the last section of chapter 16. And the objectives are we're going to kind of make use of those electronegativity values that we talked about before, and we're going to talk about different types of bonds. There's more than one way you can have a covalent bond. I've already told you can have single covalent, double covalent, triple covalent, a coordinate covalent, where one atom gives both of the electrons. But within those bonds, you can also have like subcategories of polarity of bond as well. All right, and then we're going to talk a little bit about weak attractive forces. So first, let's talk about polarity of bonds. The bonding pairs of electrons in covalent bonds, like here, these are bonding electrons where the lines are, they can be shared unequally. One atom might pull stronger than the other one. Now, if it's completely equal, which would be the case in like a hydrogen-hydrogen bond, they're the exact same atom, so they're going to want the electrons equally as much. This is a completely nonpolar bond. But if they're shared unequally, which is especially true in water, oxygen wants the electron more. So what we end up with is a polarity, and we usually draw it like this, where you have a positive because oxygen wants the electrons more. They're pulled towards the oxygen, and the arrow shows which direction the electrons are being pulled, and you'll see the little plus at this end. So it tells us that water has a negative and a positive pole, which is important for how a lot of not just water, but polar compounds can actually have polar interactions with other compounds because of this difference in electrical charges. So this results in a polar bond. There's an animation here that kind of shows that, but you can look online for animations. I'll probably link some as well. But that tells you that. Now, I also want you to understand that polar bonds does not mean polar molecule. Now, water is a polar molecule because of the structure of water. I have a polar bond here, and I have a polar bond here. And if I add these two polar bonds together, I get an overall polarity. But here, with carbon dioxide, each of these bonds is polar, and oxygen wants the electrons a little bit more. But because of the symmetry, if there is symmetry, they cancel each other out. And this is a polar bond and a nonpolar molecule. Okay? So symmetry determines whether the molecule is polar. Electronegativities determine whether a bond is polar. So for instance here, between hydrogen and oxygen, there's an electronegativity difference of 1.22. Between carbon and oxygen, it's 0.89. And here if I do formaldehyde, you have a carbon-oxygen and. So you'll notice that formaldehyde is very polar. Water is polar because all the arrows are pointing in the same direction. Carbon dioxide is not polar because the polarities cancel each other out. Now these numbers come from the differences in the electronegativity values of those atoms. And this is what you want to know. If you have an electronegativity difference of less than 0.4, it is nonpolar. If it is between 0.4 and 2, it is still a covalent bond, but it is polar, and you can have different levels of polarity. If the electronegativity difference is greater than 2, which happens to be the case between every metal-nonmetal combination, metal-nonmetals will always have an electronegativity difference greater than 2. Therefore, one of them, the nonmetal, will take the electron. It's like, I want it more than you, so it's mine. So the electronegativity difference that we learned about a couple chapters ago is usable in determining the polarity of a bond. And I will give you two compounds. I will tell you what their electronegativity, or two elements. I'll tell you what their electronegativities are. And then I'll ask you, is a bond between them polar or nonpolar or ionic? That'll be like a test question. Okay? Now, so that's basically bonds. And if you have polar molecules, that is one way that two different molecules can be attracted to one another. In fact, if you have two nonpolar molecules, they can be attracted to each other. by weak covalent interactions. So there are many forces that can determine whether or not compounds come together or attracted to one another. And these are some of the forces. First of all, within a compound you can have ionic bonding. And you can have a polyatomic ion, which is like a molecule with a charge that will undergo ionic bonding. Covalent bonding is a type of bonding between two atoms. And these are designed so that you understand that ionic bonds are the strongest bonds. I'm giving you the strongest bond first. Covalent bonds are weaker, although some triple covalent bonds are just as strong as ionic bonds. So triple covalent is the next strongest, double covalent, and then single covalent. The next type of attraction that can form molecules is network solids. And what a network solid basically means is that, like a diamond, this carbon is, I can have this carbon is bound to this carbon, 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 is bound to this carbon. These might be bound together. There'll be another carbon. They might be bound together. Because every carbon can have 4 different covalent bonds, a diamond can get all of these carbon and this would be a 3-dimensional structure. This is a network solid when you have many covalent bonds kind of interlinking something. And this forms, and what happens is I can get, and what if I have, so this is one, and then over here I have another carbon, 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 and it's not actually bound to this structure, but due to other things, it's kind of held in place by the structure. It's kind of like 2 pieces of a puzzle coming together. There's not necessarily an interaction between them, but they're held in place simply by the fact that they can't get out anymore. That's kind of like a network. Think about it as like joining your fingers together like this. That's a network solid. The next strongest bond is a hydrogen bond, which is a type of van der Waals interaction between dipoles. But because of this structure of water, because it's so polar, because these electrons are just sitting out freely, and because basically what you have, and let's draw the hydrogens out here, both of these electrons are way out here, and you have these positive protons that are just kind of exposed. Because you have these exposed hydrogens that have a proton basically exposed, because the electron has been pulled towards the oxygen, this becomes stronger than most polar interactions because there's no shielding. If I had something larger like sodium was somehow bound here. So if I had a sodium oxygen linkage, that sodium is, that positive core is shielded because you still have other electrons shielding it. But hydrogen has no shielding. It's just a proton. And because of that, it has stronger polar reactions. And that's why hydrogen bonding is special. And then you have van der Waals forces, which are weaker attractions, like dipole interactions. You have 2 polar compounds that come together, but that don't involve hydrogen. Same kind of reaction, just not hydrogen. And then dispersion is caused by the movement of electrons. So just even something like methane that's nonpolar, or carbon dioxide, which is nonpolar, the electrons are still moving. So they do generate very weak magnetic fields that can attract each other. So what do you need to understand here? You need to know the definitions. Like, what is an ionic bond, covalent bond, network solid, hydrogen bond, van der Waals forces are those weaker dipole interactions. You need to definitely understand why hydrogen bonding is stronger, because of that basically being an exposed proton. And you just need to know the order of these, which one is the weakest and which one is the strongest. Now, what do I mean when I say dipole? A dipole is a pair of equal but oppositely charged poles separated by distance. That's all it means. Hydrogen bonding is a special type of dipole interaction. It is not a covalent bond. Hydrogen bonding is not a covalent bond. It is a dipole interaction, but it is still pretty strong. So a dipole is like you have a nitrogen-hydrogen polar bond, an oxygen-hydrogen, or a fluorine-hydrogen. These are very polar bonds, and they create dipoles. And hydrogen bonds can have a strength of 4 to 50 kilojoules, so that's actually a really strong bond. but it is just a dipole interaction. So that's what I want you to get out of this chapter. Understanding polarity, and really what is the strength of different attractions, and when do I know that a bond is polar or not? And that finishes up chapter 16. As always, let me know if you have any questions.